Thank you. I'll be talking about an arithmetic that was motivated by Google's Android calculator, but has also been used for floating point testing, for testing of floating point math functions. I'll focus on the calculator application here. So, wait a second. Technical glitch. Why can I not advance the slides?
You may have focus. You might want to exit the full screen and then rejoin it. Yeah, you probably don't have focus.
Oh, okay. Something worked. Okay, good. So floating point has the advantage that it's fast. It has a precise definition, but one that's rather unintuitive. So in particular, it's not associative, for example. Sometimes even really simple problems generate somewhat surprising answers. If you ask the two most popular web search engines what the tangent of arctangent of 10 to the 20th is, they both agree that it's about 1.633 times 10 to the 16th, though not quite, which is a bit odd. We all know that if we take the limit as n approaches infinity of 1 plus 1 over n to the nth, that should be e. If you try to test this on a calculator, you'll get sort of somewhat consistent answers with that. So for n equals 10 to the 10th, that more or less works and gives a nice answer. For n equals 10 to the 20th, somehow you then get a completely incorrect answer. And we'll actually sort of use that as the standing example here. So what we want for calculator arithmetic really is, as our first goal, is we always want the result to be accurate. We want an error of less than 1 in particular in the last displayed digit, no matter what the computation. And we basically take this as an absolute requirement. It turns out that once you do this, that has some other nice consequences. You can also get scrollable results. So as you'll see here, hopefully, if the technology cooperates. So in order to accomplish that, the candidate solution is to use what's known as the recursive reals, or sometimes the constructive or computable reals. Basically, what you do here is you produce a representation of the exact result, and that representation then allows extraction of arbitrarily precise approximations from that result. This turns out to be almost good enough, but not quite for our application. So since I imagine not everybody may be familiar with this, here's the one slide overview of what recursive real arithmetic is. We basically represent a real number as a function that's capable of producing approximations. So in the really simplified version on the slide here, I give the function an argument n, and it produces a rational approximation that's accurate to 2 to the nth. So the interesting values of n here are usually negative values, and sometimes large negative values. So to add two numbers x and y, then we have to compute another function associated with x plus y, is just the one that approximates the arguments to slightly more precision and then adds the arguments. And you can do the simple error analysis here, and that's good enough. The actual version that we use doesn't use rational numbers as the result, but scaled integers instead. The rub here is that if you try to compare these, well, there's an obvious way to compare these. You basically have, if given two numbers, you just go ahead and evaluate both numbers to increasing precisions until you can definitely determine that they're different, and you can tell which one is bigger. And if they're not equal, that works fine. The problem is this process diverges for equality. And in fact, it's fairly easy to show that for general recursive reals, equality is in fact undecidable. It turns out that actually equality is decidable for most calculator operations. On the other hand, it's not practically so. There are no algorithms that actually do this effectively in a way that we could possibly use in a calculator. So the consequences of having these potentially diverging comparisons in the calculator is that, well, even in simple cases, we can't identify domain errors. We can't identify that something is a division by 0. So what will happen in practice is the division itself will diverge, and it'll eventually time out, which isn't completely awful, but it's not good. The calculator can't truncate values correctly, which is annoying because scrolling looks funny if you can't do that. Probably the most serious problem here, somewhat surprisingly, is that if you try to use the calculator to add up your bar tab, you're going to get a strange looking answer that's technically correct, but not what you wanted. You're going to get lots of trailing zeros and the ability to scroll through an infinite number of trailing zeros at the end, which is not really desirable. So what we do instead is, since we can't always get decidable comparisons, but we can actually cheaply get them in many cases, and we actually seem to be able to get them in the cases that people actually care about, we basically provide a way to get those comparisons when we really expect them. So our real type provides an is comparable function to which you give two representations of real numbers. And if is comparable returns true, then you guarantee that the comparison will always terminate, even if x and y are equal. What makes this interesting is that a bunch of classical number theory results basically give you the handle to often return an is comparable value of true. If that weren't the case, this wouldn't be interesting. So the actual representation we use for real numbers is the following. We represent a real number as a bounded rational factor, as a rational number times an arbitrary recursive real factor. And whenever possible, we use a simple symbolic representation to describe the recursive real factor here. This is significantly redundant in that if we just constrain the bounded rational factor to 1, we can still represent all numbers. On the other hand, this potentially gives us a lot more information, which turns out to be quite helpful. We use bounded rationals here rather than general rationals in order to avoid certain performance anomalies if these things get too big. The simple symbolic representation is really simple. It's basically one of the following here. It's the constant 1 or pi. Again, remember that this can be multiplied by a rational number. Or it's one of the small finite collection of functions applied to a bounded rational number. In addition, it turns out we tweak this a little bit to sometimes keep track of whether numbers are known to be irrational. When we operate on these numbers, we try to maintain the symbolic representation of the constructive real factor whenever we can. When we can't, we can always fall back. This representation allows a fallback to just a rational multiplier of 1 and an arbitrary constructive real number. So the core observation that makes a lot of this work is that so long as we have a symbolic representation in this form, we can normalize the number in such a way so that if the number is rational, it's obviously so, meaning the constructive real factor is 1 and it has a symbolic representation that says it's 1. This relies on some, as I said, some classical number theory results. In particular, the Lindemann-Weierstrass theorem is very helpful, and Niven's theorem helps for trig functions. So the consequences here, as far as comparisons are concerned, so long as the number representation includes the symbolic representation, they're either both known to be rational, in which case we can just compare the rationals, or in the other case, if they have other representations, we know that they're irrational, and in general, in the usual case, we can compare them as well, because we can typically conclude based on the symbolic representation that the numbers can't possibly be equal, and thus they can be safely compared by just evaluating to increasing precision. So in particular, if we're comparing a known rational to a known irrational, we know that the naive comparison process will converge. So using this approach, we've used this approach in Google's Android calculator for a while now. It's actually, the implementation is fairly compact. It's about 6,000 lines of code or so. We basically haven't been getting any complaints about the arithmetic implementation, which distinguishes it from an earlier floating point implementation. The only complaints we keep getting is about calculator expression parsing, which turns out to be something that nobody agrees on. It produces results in a perfectly reasonable amount of time for this kind of application. It turns out the symbolic representation actually can be useful at times, so we started to expose that to users under certain circumstances as well. So with this approach, not only can we approximate E in that formula by using n equals 10 to the 100th and get the correct result, we can actually ask how far is that answer off? How much does it differ from E? And if we multiply that by 2, we happen to get an interesting answer. We can in fact use larger values of n, and this is sort of near the limit of what will happen, what the calculator will still support on a phone before running out of time. On the other hand, we can still get a reasonable decision procedure, which allows us to identify domain errors in the easy cases like this one. So we can guarantee exact answers with standard mathematical properties. We can get arbitrarily precise approximations with decidable equality where it's expected, and the cost for all purposes is not an issue. It actually turns out this is sometimes less expensive than the recursive reals for reasons that are discussed in the PLDI paper that describes this. I think this is actually a good match for arithmetic in general that's directly visible to users. And as I said, we've also used it for floating point math testing. Thank you.